So can you all hear me and see this?
Yes, sir.
So today so last time we saw the definition of projective modules, which was this, that R be a ring, R module is said to be projective if given any surjective I linear map from A to B and an I linear map from P to B. So there you can lift the map from P to B to P to A. Yeah, so you should think of this diagram such that this diagram commute. So lift meaning you can find phi tilde from P to B such that when you compose it with G, you get the phi you started with. Okay, and then we saw these were equivalent to a few more conditions. So I wrote four of them. So P is a projective R module. This is equivalent to saying that any short exact sequence with ending in P splits, and this is equivalent to saying that if you have a short exact sequence of R modules A, B, C, then if you home it with P, it remains short exact sequence. Yeah, so you get an induced map from home PA to home PB to home PC, and home 0 P0 is 0. Yeah, so any there is only one only one R linear map from P to 0. There is only one map essentially from P to 0. Yeah, that is you send everything to the 0 element, and similarly there is only one map from 0 I linear map, this time I linear map from 0 to C, which is 0 has to go to 0. Yeah, so this the induced sequence is this, and if P is projective if and only if this sequence is exact for any short exact sequence ABC. And a special case of 3 is this 4. So if you have a surjective I linear map, then this map should be surjective. Yeah. So this is a special case because you can make a short exact sequence out of it, right? You put a K here and this is surjective, so it becomes a short exact sequence. And from 3, you know that the induced sequence will be exact, which is same as saying that and this map home PB to home PC is surjective. And then I forgot, this was the most popular one, equivalent another definition of projective. So P is said to be projective. There exists an R module Q such that P plus Q is a free R module. Yeah. So this is also equivalent. So we'll show that these 5 are equivalent, and so you can take any one of them as the definition. Okay. So and we saw, for instance, free modules are projective. Yeah. So if we had put 5 as our definition, then that would be immediate. Yeah. But anyway, even with this definition, we saw that free modules are always projective, and we'll see some examples of. So we use this splitting kind of. I don't know which. Yeah. So so basically it has a basis. So giving maps is slightly easier once you have a free. Is straightforward. You just assign basis elements some value. So let's see a proof of this. So 1 implies 2. So we also last time saw splitting is equivalent to a bunch of things. Yeah. So right splitting is equivalent to left splitting, and it is equivalent to saying that the middle guy is a direct sum of the left is isomorphic to the left and the right, direct sum of left the module on the left and the module on the right. Yeah. Okay. So 1 implies 2. So what is so one is the definition of projective module, and 2 is So 2 is the splitting statement. So we have to prove that this short exact sequence splits. So this is a short exact sequence. You take the identity map from P to P, and note that A to B is surjective. Yeah. Sorry, B to P is surjective because it's a short exact sequence, right? So that tells you that by definition of projective modules, since B2P is surjective and you have a map, identity map, you can find a map S from P to B such that this diagram commutes. Yeah, which implies that S followed by whatever this map was. So maybe I'll just give some name here. Um, G, S followed by G is identity. Yeah, which is same as saying this is a splitting. Splitting precisely, remember, is a map from P to B such that S followed by G is identity, a linear map. Okay. So this in this existence of S is guaranteed by the hypothesis that P is projective module, or by this definition of projective module. Okay. Okay, so I'll assume it's clear. You have any questions? Okay, no. Okay, so that's 1 implies 2. So I'll plug in this number 5 somewhere between 2 and 3. Yeah, so 2 implies 5, and then 5 implies 3, and then 3 implies 4, and 4 implies 1. So let's see 2 implies 5. So we know that the short exact sequence, any short exact sequence ending in P splits. We want to show that there exists a module Q such that P plus Q is free R module. Yeah. So the way to get a free R module is so to be able to apply this, we'll have to cook up a short exact sequence, and and the way to cook up that short exact sequence is you put a free module F. Yeah. And remember, there was this criteria for splitting means B is direct sum of A plus B. So if we make sure B is free, then we'll be done using the splitting criteria. And we can always find a linear surjective map from a free module to P. How is this possible? How do you cook up such a linear map from some free module?
I mean, we can take F to be means the basis of F to be all elements of P or the generators of P, and
Exactly. Yeah.
then
So you just take you can take a generating set of P if you want to be minimal. Yeah. So you take any generating set of P and take a free module over this generating set, and then and then you send these basis vectors to those elements of P, and this will define an linear map from this free module to P, and it's obviously going to be surjective, right? Because this generates P. Yeah. So we'll get a linear map, a surjective linear map from this, and we declare Q to be the kernel of E. Yeah. Then we'll get the short exact sequence, 0 to Q to F to P, and we have a splitting from P to F. And because of our hypothesis 2, and hence the free module. So by that equivalent criteria we saw last time, this free module is isomorphic to the direct sum of P and Q. Yeah. So we get so this K is basically Q kernel. Okay. Okay, so this is what we saw last time. The splitting is equivalent to saying that the middle guy is direct sum of isomorphic to direct sum of the kernel and the right hand side. Okay, and so that proves 2 implies 5. Now we'll show 5 implies 3, and so 5 implies 3 is a yeah. Um, so we want to show that if you start with a short exact sequence, then if you do home, then it remains short exact sequence. Yeah. So recall that. So this you may have seen in the earlier lectures, if you went through those lectures, that home m plus n comma a is isomorphic to home ma plus home na. Yeah. So the map in this direction. What is the map in this direction? You start with some linear map like this, then you restrict it to phi restricted to m, because m is a submodule of this. Yeah, comma phi restricted to m. So this is the map in this direction, and you can find a map in the other direction as well. So if you are given phi1, phi2, so phi1 in a map, a linear map from M to A, and phi2 a linear map from N to A, then you can cook up. Yeah, so phi of M comma N, you can declare it to be phi1 M direct plus. So phi1 M is an element of A, and phi2 M is N is an element of A. You can add them. Yeah. So so this gives you a map from so phi1 phi2 going to this phi is the map in the other direction, and you can see that both of them are linear and they're inverses to each other. Okay, so we'll use this fact essentially to show 5 implies 3. So suppose ABC is a short exact sequence of R module. Now P is P is a R module, and we know that there exists Q such that P direct sum Q is a free R module with basis B. Yeah. So first let's home with F instead of P. Yeah, because F is just P plus Q, and we'll use this identity later on. So first let's home with F. Then we get a sequence. Um, sequence home FA, home FB, home FC, and 0, 0 here. And the assertion is this is exact. Yeah. So why is this exact? So the point is home FA is basically B copies. B is the basis. B copies of A. Yeah. So if B had finite, so remember. So so maybe I should write a few more letters here, words here. Yeah. So remember, home RA is just A, and hence using this fact this m plus n, home m plus n comma a is home ma home na. From there, so maybe this is in further brackets. This implies home Rn A is A power n, or in general for any basis you'll get the size of the basis. Yeah. So home FA is just A power B, where B is the basis. Home FB is B power B. Home FC is C power C. So this is exact because this happens, and so what you're asking is whether this is exact or not. And here the map is basic. The map will be component-wise map. Yeah, if you do all the identification, you'll get that. So you think of it as 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 size of B tuples of A. Yeah, of elements of A, and size of B tuples of elements of B, and size of C, B tuples of elements of C. Yeah, and or if you want to think of it as formally, then this is set of functions from B to A, this is set of functions from B to C, and this is set of functions from script B to C. Yeah, and then the natural, then you know what the natural map is. Yeah. So of course, if A to B to C is exact, then you just take the direct sum of those, and it remains exact. Yeah. So this is it. Okay, is this clear? You want more explanation? Okay, so you can think about it. If this is not clear, then you can ask me. So once you know that this is exact, then you plug in plug for fp plus q and use this identification. Use this identification to conclude that this sequence is also exact. So you replace home f comma a by home p comma a plus the exam home q comma a, home p comma, and then the second term by this and the third one by this. Yeah. So this is also short exact sequence because the top one was. And now if you think about it, under this map, home P comma A will land in home P comma B, yeah, because these maps are given by composition. Yeah? So if you start by some map so this is a pair of map P comma A to comma Q comma A, yeah. So it will go and then if you compose it with the map from A to B, then of course a map from P comma A will land in a map in home P comma B, yeah. And similarly a map from home P comma B will land in a set of maps from P comma C, home P comma C, yeah. So this will split into two a short exact sequence, and we are only interested in the top one. So what we get is this. This guy is a short exact sequence. Okay. So this I've written somewhat sketchy, but you can make this completely rigorous. Once you write down the identification between home FA and home P comma A plus home Q comma A, exactly, then you can make this completely rigorous. Okay, any questions? Okay, so this is 5 implies 3, and then let's go to 3 implies 4. So of course, as I said, 3 implies 4 is a special case of 3, so 3 implies 4 is trivial, and finally 4 implies 1. So we have to show that so 4 was so 4 and 1 are more or less the same statement, yeah, just disguised. So 4 says that if you have a surjective R module homomorphism, then home set of R linear map from P to B to a set of all R linear map from P to C. This map is actually surjective. So this is 4, and we want to prove 1. So you start with a surjective. So one says that given a surjective map from A to B and a linear map from P to B, you can lift this map from P to B to P to A. Yeah. Well, so 4 implies that you have a surjection like this, because A to B is surjective. So unfortunately in B, we have used B to C instead of A to B. It doesn't matter. Yeah. So 4 says that this is surjective. So that means given this linear map phi from P to B, there exists a linear map C from P to A such that F compose C is phi. Yeah, that is what this induced map home P comma F is. Yeah, you pre-compose by F. That is how you get this map. So that is same as saying that you can lift this map phi from P to B to P to A. Yeah, so that is so that implies that P is projective. Okay, so that completes the proof of this proposition, which writes down the various equivalent conditions of projective modules. Okay. Are there any questions? Okay. So I hope. So do ask me if you have questions or comments or something. So that doesn't feel okay. So actually, so when we were talking about home, I had mentioned that home is always left exact. Yeah, the only exact this surjection at the end is a problem. Yeah, so even in this statement about homes here, um, even in here, the issue is not about exactness on the left. The issue is about the exactness on the right. That is what one has to take care of. Okay. So because exactness on the left is always true. So that's the next proposition. Um, so no, home is left exact, and and this is true for both kind of functors. Yeah. So not just home m comma a, but also home m comma c. Okay. So so let me take a 1 minute break and you read this and I'll try to sort out there's some issue here. I'll sort out. So just read this statement and I'll get to the proof uh, in 1 minute. Okay. So let's try to prove that this is always left exact. So is injective. So that means F lower bar is injective. G lower bar is has the property that its kernel is same as the image of F lower bar. And similarly, so remember this, when you home into this module M, it becomes contravariant. Yeah. So you get a map from a home CM to home BM, and then you get a map from home BM to home AM. Yeah. So this is G tilde and this is F tilde, and this is exact. Okay. So also at least some of them, and I'll leave it for you guys to verify. Yeah. So maybe I think we'll start with showing F lower bar is injective. So I think we had already showed G tilde is injective in some sense, yeah, when we were doing some examples. So, but anyway, let's see. So we'll show F lower bar is injective. Yeah. So to show F lower bar is injective, F lower bar is this map. Yeah, maybe keep it this way. So F lower bar is this map, home MA to home MB. Yeah, so to show that F lower bar is injective, we have to show that if something becomes zero, then if you apply F lower bar, it becomes zero, then you must have started with zero. So F lower bar of phi is F composed phi. That is how the induced map look like. And if this is zero, then that tells you that F composed phi is zero. So that tells us that F composed phi of M is zero for all M in this module M, capital M. But F is injective. Yeah, we have started with this short exact we have started with this exact sequence, 0 to A to B to C. So usually in the books, it's in some books they just write short exact sequence A, B, C, 0. Okay, but you don't need for the first statement don't need the surjectivity of G, and for the second statement you don't need the injectivity of F to conclude these two statements. So, but in spite of surjectivity of G, you can't conclude the exactness on the right. Yeah, so that is what. And in spite of the injectivity of F, you will not be able to conclude the surjectivity in the second statement as well. Okay. Okay. So since F is injective, you get that phi m must be 0 for all m in M, which implies that phi is 0. Hence, F lower bar is injective. So, and as I argued, G tilde is injective, just followed from the surjectivity of G. Yeah, so this kind of argument we had seen when we were discussing that example. So let's ignore that. Now, second thing we need to notice is that G composed F is 0, irrespective of whether you're looking at 1 or 2. Yeah, because both are exact. So in fact, what we know is the image of F is equal to kernel of G, not just contained in. So G composed F is 0. And we know that home is a functor, which means home of m comma G composed F is same as home of m comma G composed home of m comma F. Yeah. So if you start with a 0 map, then home of m comma 0 is going to be the 0 map. Yeah. So this is the 0 map, and this 0 map is a composition of these two maps. So it's composition of these two maps. So if which is and these two maps are G bar composed F bar. So if G bar composed F bar is 0, what do we know? That we know that the image of F bar is at least contained in kernel of G bar. Yeah. So it is at least a complex. That part is clear. Yeah. So the only thing we have to prove is that the kernel of G bar is contained in kernel image of F bar. Okay. So you start with some element in kernel of G bar. We want to show that it's actually in image of F bar. So if you start with some element in kernel of G bar, that means G bar of phi is 0. But what is G bar of phi? Is just G composed phi. Yeah, like here, F bar of phi is F composed phi. So similarly, G bar of phi is just G composed phi. And we are given that since phi is in kernel of G bar, G composed phi is 0. So what does that mean? And that means G composed phi of M is 0 for all M in M. So that means that phi m, so G applied to phi m is 0. So that means phi m is in kernel of G for all M in M. Yeah. But the sequence is exact. A to B to C is exact at B. Yeah. So that tells you that kernel of G is same as image of F. Yeah. So this implies that phi of M is contained, it belongs to image of F for all M in M. Yeah. So phi of m is so you declare I want to get a map. I want to show that phi is in image of F. So I have to cook up some map from M to A such that when I apply F bar to it, we get phi. Yeah. So this is my map C. So Cm you declare it to be F inverse of phi of M. Yeah. And it makes sense because phi of M belongs to image of F and F is injective. Yeah. So F inverse, there is a unique element. So F inverse is well defined on its image. So Cm is F inverse phi of M, and since phi is R linear and C is injective R linear, this composition is also going to be R linear. Okay. So C is an R linear map, and the maps the domain of this map is M, and it lands in A. Yes, F inverse of phi of M is A, is an element in A. So C belongs to home R MA, and F compose C is phi. Is that clear? And hence you get that phi is in the image of, and hence kernel F tilde is image G tilde. Yeah, is that okay? Any questions?
It's okay, sir.
Okay, good for everyone. Okay, good. So let's. So I'll not do this the other one, F tilde and G tilde one. So you just do it. It's a same step. Yeah. So again, kernel is contained in image. Will follow from functoriality of home, and then the other statement you do it element wise. Okay. Okay. So uh, uh, this is about projective modules. Some basic. Okay. So maybe some examples. So some more discussion on projective modules, and then we'll see. Okay. So have you guys already seen all this, or is this useful, or um, okay? So anyway, let's just go through this, and we'll worry about it. Okay. So over Z, what do we know about finitely generated Z module? When is a finitely generated Z module projective? Can you characterize projective Z modules? So what do you know about finitely generated G modules? What can you say about it? How do they look like?
Well, it has to be free, right?
Yeah, so how do you show that?
So finitely generated free modules. So we have structure theorem.
Yeah, exactly.
So then the torsion part cannot be a subgroup of free one.
Yeah. So the point is you use the structure theorem. Yeah. So the structure theorem. Yeah. Sorry. So the structure theorem says that um, that it has to look like Z power R, where R is the rank plus some torsion part. Yeah. Tm. So the Tm must be 0. Yeah. So if and only if because it for it to be free, you should be able to take it should be a direct summand of a free module. Yeah, and the torsion module can't be a torsion Z module can't be a direct summand of a free Z module. Yeah. So if and only if it is free. Okay. So here, so it is not a trivial statement. You are using structure theorem of modules over PID. So this is true not just for Z, but any PID. Yeah. So over any PID, a finitely generated R module is projective if and only if it is free. And this is equivalent to saying it is torsion free. Because torsion free implies free. Yeah. If it is finitely generated. How about so one direction is always true. Yeah. So if R is an integral domain and M is a projective R module, then what do we know about torsion of M? What can you say about tau m? Tau m is going to be a submodule of M, right? Because R is an integral domain. That part we know. Yeah, what submodule can it be?
It's a submodule of a C module.
Yeah, but you can specifically say it's a torsion module, right? So when can a torsion module be a submodule of a free module over an integral domain? It has to be the zero module, right? So,
Mm-hmm.
so free module doesn't have any torsion over an integral domain. It cannot have a torsion, right?
Okay.
So it has to be the zero module. That's how we decided that the torsion part has to be trivial because you can't include it in the first one. You can't include it. So a free module has no torsion over an
Mm-hmm.
integral domain, right? So yeah, I mean, at least R doesn't have any torsion because R is an integral domain. A times B is zero. That means either A is zero or B is zero.
Mm.
So I mean, so if you think of R as a R module, then you take any non-zero element of it, then the only thing that can kill it is the zero element. Yeah. So non-zero element can't be torsion, and this is true for not just R but any free R module. Okay. So this part is okay. What about Q as a Z module? Is it projective? Does Q have torsion? What is torque Q? Yes. What is torque Q?
Zero, right? Because
Yeah. So torsion is certainly zero, right? Because you can't kill any element, non-zero element of Q by multiplying with an element of Z. So it is torsion free, but is it projective? Is it free? First of all, is Q free Z module? Is Q a free Z module? Yes, Rahul? Anyone? Is Q a free Z module? What do you think? Make a guess if you don't. I mean,
So any two elements of Q can be written like can be multiplied by suitable integers and the linear combination will be 0.
yeah. So it can't be. So at least if it were to be free, it has to be singly generated. Yeah.
Yeah.
It can't be generated by more than one element. So that tells you that it has to be um, it can't be free, right? Because singly generated free module means it has to be isomorphic to Z, and is certainly not isomorphic to Z. Okay, so it's certainly not free. Yeah. How about projective? Is it projective? So the same reasoning tells you it can't be projective as well. Yeah, because you know. If it were projective, you would be able to embed it in some free module, but then you can't find a basis, yeah, because any two elements of that will generate. So Q is not a projective. Uh, sorry. So. But not projective. Okay. So here the hypothesis that it's finitely generated is important. Okay. So yes, but Q was also not free. Yeah, so we still haven't seen an example of a projective module which is not free. So over Z mod 6 Z we can so your ring is Z mod 6 Z. Then over this you can cook up a projective module which is not free. So can you make a guess which module will be projective but not free? So what's an example of a non-free Z mod 6Z module? Any?
Integers.
So integers. Integers is not a Z mod 6Z module, right?
Z
Because
mod
there is,
Z mod 3Z becomes Z
yeah,
mod
Z mod 3Z, you can say it's a Z mod 6Z module, but Z is not a Z mod 6Z module. You can't give, I mean, 6, if you, it should be 6 torsion. Yeah. Every Z mod 6Z module will be 6 torsion. So if you take any element and add it to itself 6 times, it must become 0. Yeah. So but Z mod 3Z is a Z mod 6Z module. You're just going mod the ideal generated by 3. Yeah. So it's actually a quotient of Z mod 6Z. So it is a Z mod 6Z module, and this is obviously not free because it has I mean any Z so it doesn't have a basis. Yeah. So one is killed by, for instance, um, uh, yeah, three times one is 0. Yeah, 3 is non-zero. Yeah, so it does not have, so it's non-zero, and you take any generator, it's annihilated by the ideal generated by 3. So it's not free, but it is projective, as I think Arghya said. Yeah, you take some with another Z mod 6Z module, which is Z mod 2Z. Z mod 2Z, for the same reason, is also a Z mod 6Z module. And you take the direct sum of this. These two is isomorphic. The sum of these two is isomorphic to Z mod 6Z, and hence it's a free R module. Okay. So this is projective. These two both are projective but not free. Or so last class I said you take K cross K, yeah, product of two fields. So this is also sort of product of two fields. So it need not be the same K. Yeah, so K cross K prime, R to be K cross K prime. Then of course K is an R module, and K prime is also an R module. You just go mod one ideal or the other ideal, and that so they are projective but not free, because their direct sum is going to be R, but individually they're not. Okay. Any questions? Okay, so there are also examples of an integral domain. So maybe, yeah, so it's not too bad, but it requires a bit of work. So let me not worry about it. But generally, projective is very close to being free. Okay, so you have to work a little bit. So these are sort of artificial examples in some sense. So number 4 is an artificial example, but one can there is a genuine reason for it to be projective modules not to be free over even over an integral domain. There is some global structure, but locally they are more or less same. Yeah. So what it means is that if you so in particular what it says is that over a local ring, every finitely generated projective module is free. In fact, this statement is true even without this finitely generated assumption, but then the proof is a little more delicate. But I mean, not with outside the reach, but it requires a little more work than has been done in the previous lectures. Okay, but this statement is more or less straightforward. Yeah, so over a local ring R, every finitely generated projective R module is free. So this is so you know why this is true, or what goes into the proof? Have you seen this statement, anyone? Who hasn't seen this statement before?
I haven't.
Okay.
I haven't.
None of you have seen. Okay. Okay. So maybe then it's probably difficult to guess how the, but it's a consequence of Nakayama's lemma. Okay. So what you do, so let P be uh, a finitely generated projective module. So what you do is start with the so let start with the smallest generating set. Yeah, x1 to xn be this be smallest length. So you can't find a generating set of a smaller length. Yeah, generating set. Then of course you can get a surjective map. Let me write it Rn. Yeah. So you think of it as ei going to xi to p. Okay. And you get some kernel. So we want to show that k is 0. Yeah. Okay. So and everything happens over this local ring R with maximal ideal M. So what does Nakayama lemma tells us? What is the statement of the Nakayama lemma? Okay, so but Nakayama lemma you must have seen, right? Because it was covered in these lecture series. Yeah.
Mm.
Okay, so the statement of the Nakayama lemma is that, or one of the consequence of the Nakayama lemma is that m times m is 0. Sorry, is equal to m, then m is 0. So m times m equals m implies m is 0. So m an R module and m an R module finitely generated. R module. Okay. And m times m is equal to m, then m must be 0. Yeah, this is what this Nakayama lemma says. Right, so yeah, so maybe so maybe one has to, so local ring generally people also mean Noetherian, so but some people don't. So over Noetherian local ring R, every finitely generated R module is free. Okay. So so now we want to so what we do is we go mod this. Okay, I see. So we haven't done tensor product. So so is there a way without the tensor product? So yeah. So yeah, so the proof is a little more work than I thought it would be. Because I mean, the point is, after the next step was to write this step, but this requires. So from here you get a short exact sequence like this. Okay, so I'll broadly tell you the idea, but so have you seen tensor products? Okay, so what you do is you tensor it with R mod M. Okay, and then there is a theorem which says that it still remains exact because P is projective. Yeah. So what you get is this is a short exact sequence of R mod M modules, and and this is so R mod M is a field. Okay, and since this was of minimal length, this will be a field of so this is generated by n elements. So this must be generated by n element. So this must be generated by n elements and can't be generated by fewer elements, because if it were generated by fewer elements, then you can lift those generators. Okay, that's also a Nakayama lemma. So this is a vector space of dimension n over R mod m, and of course this is just R mod m whole power n. So this is also a vector space of dimension n. So that gives you that k mod mk must be 0, i.e. k equals mk, and then you apply Nakayama to hence k is 0, because k is remember k is a submodule of a finitely generated R module, is submodule of Rn, and hence it must be finitely generated because you're over a local. Okay, so this is the proof, but that requires yeah, I don't know if I can do this without tensor product though. Okay, so anyway, so once you see some tensor product, you will be able to fill this gap. But important thing to know is that projective modules locally look like free modules. Okay, and as I said, this is true even without this finitely generated assumption. So and hence it's true even without this Noetherianness assumption. So in this proof, you need Noetherian and finitely generated, but the slightly more subtle proof has it without all these assumptions. So locally, you should think of projective and free as same, but over a local ring. But of course, over a bigger ring, it's not true. Okay, so this is all I wanted to say about rings and modules for you guys too. Okay, and so on. 1 second. So let me just end this recording. How do you end the recording?